best chairman one speaker can dream of. Thank you very much. So, Mr. Chairman, my fellow speakers, ladies and gentlemen, thank you very much to the organizers for giving me this opportunity to talk about geophysics-driven transformation, which enables smarter exploration and sustainable energy infrastructure. As Mr. Chairman mentioned, and after that Mr. Negi also mentioned, that when we are talking of clean energy, it is not just enough to look at the carbon emission at the time of utilization of that particular energy. What is also important is to look at it from the entire life cycle. I'm a geophysicist. I'm more concerned about the life cycle where we talk about investigations and exploration. So the technology I'm going to talk about today is basically linked to making it more environment friendly, making it faster, and getting much more data for larger areas, which can really reduce the footprint of this particular stage of the energy. A very brief introduction about the company which I represent. Parsons is a geophysical company. We are the largest near-surface geophysics company in the country. But more than that, we are known for bringing various innovative technologies from time to time in the country, which are listed here. I'm not going to read through it. I'm particularly going to talk about passive seismic tomography for oil exploration, oil and gas exploration. And since Madam Shubha is sitting here, and we were just discussing in the lunchtime, the same technology also can be used for geothermal exploration, which again needs much deeper information, all right? So this is something which I had the privilege of introducing in the country in 2008, and after that we have done a number of projects. We have offices in India, and we have offices in Bahrain, Saudi Arabia, and Singapore, so we are an Indian multinational. And we are working in more than 14 countries around the world. I'm a geophysicist by profession, as I said. I graduated from University of Roorkee, which is now IIT Roorkee, in 1990. So it has been 35 years of journey in the field of geophysics. I started my career with government. I was with UP government, then moved to atomic energy, but 95, something happened to me. As I say, some bug coming in your brain, and I turned an entrepreneur. But honestly, I'm enjoying the journey, so no complaints. All right, coming to the topic. So we are going to talk about passive seismic, right? So as we say, get active, choose passive. Because these advanced geophysical methods, such as passive seismic tomography, embody digital transformation by generating high-resolution data-driven subsurface models using ambient seismic source. So what it means is that we all know the conventional seismic, where we are using active sources. We are using explosives. There's a lot of movement of manpower, equipment is involved in the entire seismic thing. But in PST, since we are relying on the passive source, we are not using any active source. And ultimately, it aligns with cleaner, non-invasive, and lower carbon exploration method. Sorry. All right. So this is a sustainable and efficient tool for deep subsurface imaging. When I say deep, I'm talking of 20, 25 kilometers deep, right? That is from where earthquakes are coming. You'll understand what it means. When we are using conventional seismic, we are sending a seismic wave from the top, which is going down, getting reflected. In this case, we are listening to the earthquakes which are coming all the time down there. And listening to these earthquakes, we are creating velocity models. So obviously, the depth of the earthquake will only determine what is the depth of exploration. So very interesting technology. It's environmental friendly, leaving no footprints, covers large area. When we say large areas, we are talking of 2,000 square kilometers being covered very quickly in maybe 6 months of time, even larger areas for that matter. Okay. How it works is, this is something not new, honestly. Even when I was studying in Roorkee in 1990, the concept of passive seismic was used by institutions like Vadia, our own Department of Earth Sciences, NGRI, to make large-scale geological models of the area. What we have done is that we have brought it from regional seismology to exploration geophysics. That is where the difference is. So here we put a very dense network of receivers. So for example, on the right on the top here, these black ones are the receivers which we are putting on the ground. They can be spaced 2 kilometers, 5 kilometers, 1 kilometer, all depending on what kind of resolution we are looking at. And we just leave them there. We leave these receivers there. They are 3-component receivers. We leave these for 6 months, 9 months, depending on the seismicity of the area. So these are a standalone recording system. Frequency range is 0.1 to 10 hertz. I'm not going into the technical details of it. And they're continuous recording time. That is 24 hours they are recording the data. And then we are bringing this data and doing our processing and ultimately creating a VP and VP upon VS model. So naturally occurring seismic signal, when we are talking about, these can be earthquakes, these can be ambient noise, and these can be even regional seismic events, right? So all these events are used when we say integrated passive seismic. Ultimately, the target is to make a 3D structural and lithological characteristic of the area of interest in terms of P and S velocity. So this is a target. So here, this entire thing is around 18 kilometers from top to bottom. And this is a, let's say, P wave velocity model which has been created, which shows different formations which are there. So this is the ultimate target of doing it, based on which, of course, you can characterize your large area very quickly. I'll just show you how environment friendly the whole thing is. Before that, why low frequency in seismic exploration are so important. So if we take a frequency of 30 hertz, more than 30 hertz is active seismic and less than 30 hertz is passive seismic. Because once we are doing active seismic, it is very difficult to acquire these low frequencies. But low frequencies are the one which will give you deeper information. Okay, and that's why we are so interested. In active seismic, it becomes contaminated with noise, attenuated, and very dangerous to generate even when you're using vibrosize. So these are the reasons why passive is adopted for that. In passive, as I said, there are ambient noise tomography, there is surface waves from teleseismic events, there are local earthquakes, micro earthquakes, etc. So right? So even a 6 earthquake happening somewhere under the sea might not be even felt by the population. But a 6.5 earthquake happening right where we are sitting and at a depth of, let's say, less than 10 kilometers, we all will be jolted badly. So it's not magnitude only that's important, but that's besides the point. So we are using earthquakes 4 and less because we are interested in point sources. As the earthquake becomes bigger, it is no more a point source, it becomes a planar surface, right? So we record these P waves and S waves using a 3-component sensor. And after that, we go for the processing. These are proprietary software which have been prepared. We work on this with the Seismotech of Greece, and University of Patras has been the academy partner where all these software have been developed. And ultimate aim is to find out, first of all, P wave velocity model in 3D, VP upon VS model in 3D, fault characterization, focal mechanism characterization. So this is what is the deliverable for this local earthquake tomography, as we call it. Then earthquake-based passive seismic, the second thing is surface wave tomography. So in this, surface wave dispersion of regional and teleseismic events are being created. So you have put your network in Assam, but the earthquake might be coming even 1,000 kilometers away from there. Using this is what we call teleseismic event. Using this teleseismic event also, by doing cross correlation, you can make a surface wave dispersion curve, which gives you again a dispersion curve up to great depth. So this is the second one which we do under integrated. Then this is very interesting. This is called reflected wave passive seismic interferometry. Now, this is because if we talk to anyone who is working in exploration in oil and gas, a geophysicist, since time immemorial, they are very used to of looking at seismic records, right? And they are comfortable with that. Anything other than that doesn't give that much of comfort. So the same is sensors which have been put for passive seismic, data can be collected from there, and near vertical arrivals are taken for each station, and based on that, this kind of zero offset virtual seismic reflection response is created, which very much looks like a seismic record, and it gives a lot of information about the structures down there. So these were earthquake-based methods. Then we have noise-based passive seismic, where we have ambient noise tomography, where we are doing cross-correlation of long-time series of pure ambient seismic noise. This ambient seismic noise keeps coming from all kind of sources. Even your sea and the waves which are in the sea is a big source of ambient seismic noise all over the world for that matter. Okay, so you can use that and ultimately create a pseudo 3D shear wave velocity model. Now comes the interesting part, installation and acquisition. Now, here what we do is, we use 3-component sensors. These are called seismic recorder. So they have 3 input channels. Sampling rate can be 1 to 500 samples per second. They are all GPS synchronized. They are ultra low power consumption. When we say ultra low power consumption, we have already done around 4 or 5 projects in India. Right now we are working in Assam on another project. We put a battery of, let's say, 100 ampere hour, and this battery actually goes for a month. So once you put the station there, it is recording 24 hours and one battery of 100 ampere hour is there for a month. You just have to visit it once to change the battery every month and take out the old memory card and put a new memory card. You don't want to do that? No problem. You can put a solar panel there. Okay, so even if you can't visit the area, it's possible to do that. And then we make small holes, 1 to 8 meters, it can be even 1 meter, and put this 3-component seismic sensor there. It is again borehole type, and this is what sensor looks like. So this sensor is actually put inside the hole by putting its north and south properly aligning. This is a simple station. And these are the real pictures of installation, you can see. So we make these small hole. We are putting this sensor in the hole, and this is a cable coming out of it. And this is a simple barrel, the blue barrel, which is used for chemicals, and we put everything there, including the battery, everything we have put inside the barrel. This is the GPS thing. And after that, we just cover the barrel. That's it. So this is the only footprint which remains at the time of data acquisition in the field. And you don't need to even go there every day. You can go there every 1 month to change the battery, pick up your data card, and that's basically it. And they are at a distance of every 5 kilometers grid or 2 kilometers grid or 1 kilometer grid, depending on what we are trying to do. Okay. So ultimately, this is, as I said, main deliverable is 3D P-wave velocity cube, 3D VP upon VS cube, seismic event location, that is for active fault identification, and focal mechanism, which also gives a great insight into the area's geology and mechanism. And of course, how can I miss that? The last one. All right, so this is, you can, I'm trying to go back. Okay, and this is the virtual reflection passive seismic interferometry, where you get record just like seismic signal. And this is one of the very beautiful example which shows the power of this technology, this method. So this is, we collect data, and right now also we are trying to reprocess our data which we might have collected 25, 30, 50 years back, right? We are reprocessing it because now processing techniques have developed. We might get something which we could not get at that time. So that is happening with all the organizations. But when we are doing migration, we are using a particular velocity model. And now if that velocity model is derived from a technology like passive seismic tomography, see the improvement. This was the data, filtered migration by whatever velocity model was taken based on limited well data or whatever. Same data has been reprocessed based on the passive seismic velocity model, and now you see how clear the various features become in the new data. So this is one of the very, very strong point that even your legacy data can be reprocessed rather than you acquiring the data again and again creating so much of carbon emission and everything, spending money and time. Also, it is possible to reprocess the data. So if we talk about advantages very quickly, it is applicable in areas with accessibility limitation, difficult operational condition. So you can see wherever last time we were working in Assam, there were places, there was no road, and flooding was there. So we used boat, we used tractors, we used everything. But we were not carrying anything except a battery, right? So it was so simple to do that. So you can practically do it in any area, however difficult it is. It is environmental friendly, as I said. So once you're doing the acquisition, this barrel is what all is visible. And once you finish your acquisition, this spot is the only thing which is visible, which also will become invisible once the grass comes there, maybe 10 days, 15 days, all right? But as of now, you can just see it. So absolutely no footprint left on the area we are working. Cost effective. It is extremely cost effective. That is, you get a 3D VP and 3D VP upon VS at a cost which is less than conducting even a 2D survey in the area. So it is extremely cost effective. And there are certain areas, for example, where you have penetration issues, where you have high velocity layer or thrust belt areas. There are areas in Northeast which are having such topography that doing a good seismic there is next to impossible, okay? All these such areas are great candidates for passive seismic. Directly interpretable results. So this particular image you see, geology has been superimposed on the VP model which has been created, and you can actually interpret the result directly from where it is. Then structural and lithological information of unexplored area. This is one beautiful and very strong part of it. VP gives you structural information. What about VP upon VS? VP upon VS basically becomes like Poisson's ratio, right? It gives you lithological information. So with proper calibration, you can actually differentiate between gas bearing, oil bearing, water bearing, if you have Poisson's ratio, which is a deliverable from passive seismic, which is not a deliverable from classic seismic, right? So this is a very strong point on this. Of course, stress and fault information, you can find out what is the fault regime in the area. Aid in well placement. So this can be used as a complementary information to minimize drilling risk as a reliable alternative source in case of poor or no conventional seismic. There are many areas, because as I said, I'm a geophysicist working in this field for 35 years. Most of the geophysicists work in oil and gas, which basically means 90% of my friends are working in oil and gas. So they keep sharing stories. In most of the areas, sometimes the seismic is very poor because of topographic challenge, because of geological challenges. And there, if you are able to do passive, you reduce a lot of risk when you are actually putting a well there. And of course, you can improve your poor quality active seismic data. Here again, you have two pictures, top and bottom, and how using this model, the improvement has been made in the way your interpretation is being done. You can also have data which is resistivity data, which can come from MT, which is density data, which can come from gravity, and you have P-wave velocity, Poisson's ratio, and now using machine learning and artificial intelligence, you can put all these four values together, compare it with the success areas, and then populate the other areas where all these four parameters are matching with the success areas. Now this is the process of artificial intelligence machine learning. More you train your model, better it will be. So with the Mr. Chairperson was very nice, giving me all the time I wanted. So I'm being a nice speaker also. I put 25 minutes for myself on my timer, and 6 minutes I still left. I'm going to conclude the presentation, So I think we both have been nice to each other. So advantages: insensitive to penetration problem due to high velocity layers close to surface or high-low, high velocity effects that are common in thrust belt zone basaltic environment. Easily applicable in areas with accessibility limitations, environment friendly, cost effective, and directly interpretable results. It gives you structural and lithological information for unexplored areas, stress fault information, aid in well placement, improvement of poor quality conventional seismic, and correlation with other availability data. So these are the advantages and benefits of this technology. I kept it short because this is a huge thing. I have conducted a 2-day workshop on the topic. So today that's not the time. But this is a QR code. If you just take out your phone, scan this QR code, it will open a very small Google form. It will ask for your name, your email ID, and put the email ID correctly, because in next 30 seconds, you will receive this presentation in the PDF format in your email ID immediately. I won't be doing anything. It's a script, AI. Even we can be intelligent. All right, so you will receive it immediately. So please scan this. Thank you very much for your attention. Thank you.